Hello, I think we can start the session now. It's already time. So I will share my screen. So today is the week 4 of the course, mathematical aspects of biomedical electronic system. And uh, as we have done in the other lectures, that is in week 1, 2, and 3, we have studied various things. If I give a brief overview of what we have studied, I think you all remember that in week 1 we have studied about biomedical signals in general, about different types of biomedical signals like ECG, EEG, etc. We have studied about different types of signals in general. The type like different types of signals like we have studied about periodic signals, we have studied about aperiodic signals, we have studied about causal signals and so on. At the same time, we have studied about different types of system and how to classify them. The last week, that's in week 3, we have studied about Fourier transform. We have studied particularly about continuous time Fourier transform. We have studied about distinction between various types of periodic and aperiodic signals. At the same time, we have solved a couple of examples to, if we have, for example, a continuous time signal x of t, we can find the Fourier transform x of omega and solve a couple of problems. Okay, so today in week 4, we will be studying about discrete time Fourier transform in general. First, we'll have a brief overview of what is discrete time Fourier transform, what are its formulations. Then we'll actually follow and continue with the different examples or numerical sets on the discrete time Fourier transform in general. So in the last week, I think in the last week I have given you a couple of examples to do it. Where those was it possible for you to solve? Okay, you can tell me like the chat section, whatever. Okay, so let's understand what is discrete time Fourier transform. So before we studied what is continuous time Fourier transform, the only differentiation between this is in continuous time the signal is continuous. That is we have values for every time interval, but in discrete time, as the denotion as the term indicates, that we have a signal for discrete steps. That is, fundamentally we can denote the signal as x of n, and the Fourier transform, or in other words discrete time Fourier transform, the signal is called the discrete time Fourier transform, and it can be expressed in some formulation which I'll show it to you. So what are the conditions for discrete time Fourier transform? The Fourier transform a discrete time sequence, that's an xn, exists if and only if sequence x of n is absolutely summable from the given time interval. So that's very important. That's the condition for discrete time Fourier transform. Otherwise, this Fourier transform for that signal x of n will not exist. So this is the formulation that we have actually. For example, if we have a x of n, which is a discrete time signal, everyone knows what's a discrete time. So the only differentiation or only difference between a discrete time signal and a continuous time signal is that the continuous time signal will have value at every time instant or every time stamp, whereas in case of a discrete time signal, the values will exist from a certain interval. That is, maybe you will have and that interval can be decided by you all, okay, or by the user. So if we consider we have a signal x of n. Now the discrete time Fourier transform of the signal can be given as x of e to the power of j omega equal to summation. That you remember, for the continuous time Fourier transform we had integration because it's continuous time, but here it's summation. That's very important. That differentiation you should keep in your head. So dt of t is given as x of e to the power of j omega equals to summation of n equal to minus infinity to infinity x of n e to the power of minus j omega n. And this equation is also known as analysis equation, because here we obtain the Fourier transform, that is x of e to the power of j omega from x of n. And this is very important to keep in our head, that this signal is actually uh, So this is very important to keep in our head that x of n is a discrete time signal, and the Fourier transform which is given as x of e to the power of j omega, and this equation where we obtain the x of e to the power of j omega from x of n is known as analysis equation. At the same time, this x of e to the power of j omega is periodic with period 2 pi, and you can see that. Okay, so DTFT will exist for periodic signal. That's very important, which we should keep in our head, and we all knew that CTFT. What is the condition for CTFT? So this is the inverse Fourier transform. For example, we have the Fourier transform, that is DTFT of a signal, and it is given by x of e to the power of j omega. So the signal x of n can be extracted from the Fourier transform signal, and it can be given by the formula as x of n is equals to 1 by 2 pi over the period 2 pi x of e to the power of j omega into e to the power of j omega n d omega, and this equation is known as synthesis equation. The previous equation where we obtained the Fourier transform, that is x of e to the power of j omega from x of n, that was called the analysis equation. This equation where you obtain x of n from x of e to the power of j omega, this is called the synthesis equation. Okay, so these are the two terminologies and the two equations that we need to keep in our head for solving the numerical problem. One is the analysis equation where you obtain x of e to the power of j omega from x of n, and another one is the synthesis equation where you obtain x of n from x of e to the power of j omega. Okay, so this is very important. Next we'll solve a couple of examples and couple of problems. Okay. So the first question, that's a very simple one, and the question and the example is x of n is equals to a to the power of n into u of n. And obviously we all know u of n is a unit step function, and as described in the previous classes, we know what is unit step. A unit step is a signal where its value lie from, yes, yes, okay, okay, sorry. Is it visible now? Okay. So this is today we'll talk about discrete time Fourier transform. Okay. So we have studied about CTFT previously. So discrete time Fourier transform is like we have a discrete signal, that is x of n, and our objective is to obtain x of e to the power of j omega from x of n. That's the Fourier transform signal. And this is the first thing, that the condition for DTFT, that is the Fourier transform by discrete sequence exists if and only if the sequence is absolutely summable. Okay, and this is the formula for discrete time Fourier transform if we have a signal x of n. So the discrete time Fourier transform for that signal x of e to the power of j omega, it is equals to n equal to minus infinity to infinity x of n e to the power of minus j omega n. This equation is called the analysis equation, and this equation where we obtain x of n from x of e to the power of j omega, this is called the synthesis equation, and this is given as x of n is equals to 1 by 2 pi integration of 2 pi x of e to the power of j omega into e to the power of j omega n d omega. So in this equation, so these two equations are very fundamental for this class. In the first equation, that is the analysis equation, we have obtained x of e to the power of j omega, that is the Fourier transform signal from the original signal x of n. And this equation where you obtain x of n from x of e to the power of j omega, that is the original signal x of n from the Fourier transform signal. This is called the synthesis equation. Okay, so this is the first question that you have, and this is a very fundamental and a very simple problem. And let me pose the problem or define the problem as x of n is equals to a to the power of n un. So u of n is what? U of n is nothing but a simple unit step function, and we all know the unit step is a function where its value lies from 0 to infinity, and it will have a constant value of 1. Okay, so for continuous time signal we have signal which is a constant from 0 to infinity. So obviously for discrete time also the signal will be same, but what is the important thing that we need to keep in our head? For discrete signal we will not have signal at every time instant, but after regular intervals. Okay, so x of e to the power of j omega, we know that the formula is equal to n equal to minus infinity to infinity x of n into e to the power of minus j omega n. But what we know, a unit step as I described lies from 0 to infinity. So we change our limits, and instead of writing from minus infinity we write as n equal to 0 to infinity. Fine. Now what we do in the next step, we take n common, that is summation n equal to 0 to infinity a into e to the power of minus j omega, and then we put n outside. Now you see this is actually an infinite series. That is this function can be broken in this manner, like you just put the value of 0 at, instead of, just replace n with 0. So what will have, anything to the power 0 is 1. So it is 1 plus, then you replace the value 1 with n, and then you will have 1 plus a to the power of minus j omega, then plus a to the power of a into e to the power of minus twice j omega, and so on. So, and this is of the form 1 plus x squared till infinity. And we all know the summation formula of an infinite series is equals to a divided by 1 minus r, where a is the first term and r is the common ratio. And what is the common ratio here? A into e to the power of minus j omega. So ultimately we have the formula as 1 divided by 1 minus a into e to the power of minus j omega. If it is not clear, you can tell me if you are not clear with this, how I have solved this problem. Okay, so this is the next question. Now let me consider I have a unit step function, and my objective is to obtain a or you can say obtain the Fourier transform for this unit step function. So you can see in the figure I have described the signal in the figure in the right hand side. Okay, this is the unit step, and the unit step is having a constant value of 1 after every time instant. So it will lie from 0 to infinity, and it will have a constant value of 1. So what we do, we write the original formula, that is a Fourier transform that we have described previously, and where x of e to the power of j omega is equals to summation of n equal to minus infinity to infinity x of n into e to the power of minus j omega n, and replace x of n with un. Then we have n equal to minus infinity to infinity u of n into e to the power of minus j omega n. But as it is a unit step, our value will lie from 0 to infinity, because a unit step, that's the property of the unit step. Fine. So we write, instead of un, we write 1, because we will have a constant value of 1 for the entire time interval from 0 to infinity. So now put the values, that is n equal to 0, we have e to the power of minus j omega 0, means e to the power of 0, which is equals to 1, plus replace the value of, replace n with equal to 1, we have plus e to the power of minus j omega, then replace n is equals to 2, then we have e to the power of minus twice j omega, then we replace n is equals to 3, then we will have e to the power of minus 3 j omega, then till infinity. So this is of the form of 1 plus a square plus a cube till infinity, and we know this formula equals to 1 divided by 1 minus r, where the numerator 1 is the value of the first term and the a is actually the common ratio. We all have studied this in our school days, how to find the summation for a infinite series. So we can replace this term 1 plus e to the power of minus j omega plus e to the power of minus 2j omega plus e to the power of minus 3j omega plus till infinity equals to 1 divided by 1 minus, what is the common ratio, e to the power of minus j omega. So this is the Fourier transform signal for the unit step. Okay, and this is very fundamental. We should actually remember this because it will help us in solving a couple of problems. Next, let us consider a delta function. Okay, and we all understand that this entire class is about discrete signals. So for an impulse function, that is del n, the value is 1 at n is equals to 0 and it is 0 elsewhere. So the impulse function will have a value of 1, that's a constant value of 1 at n equals to 0, and the value will be 0 elsewhere. So writing the original formula again, that is x of e to the power of j omega equals to n equal to minus infinity to infinity, replacing x of n with del of n into e to the power of minus j omega n. Then we have to recall the original definition of the impulse function. So what I said, the impulse function for discrete signal, that's very important for discrete signals, will have the value of 0, will have the value of 1 at n equal to 0 and it will be 0 elsewhere. So what we do, we write instead of del of n we write 1, and this value of 1 will lie at only n equal to 0. So we put n equal to 0, that is which is equals to 1 into e to the power of minus j omega into 0, which will become e to the power of 0, and we know anything to the power 0 is nothing else but 1. So what we have at the end, we have the Fourier transform, that is, or in other words, the discrete time Fourier transform for a discrete time delta function which is equals to 1. So these two formulas are very much important for this class. First one is the discrete time Fourier transform for a step function, and this is the discrete time Fourier transform for an impulse function. Okay. So let's solve another problem which is of the similar line, which is actually a signal x of n which is equal to u of n minus k. U is again, I am just telling you, u of n is again the unit step function, but here the problem for us is not the direct unit step but a shifted, or in other words a time shifted unit step function. So before solving this problem, let us actually look into some of the properties of discrete time Fourier transform, then we'll actually go back to the problem again. Okay, so this is first property. Let us look into some of the properties. That is, the first properties is time and frequency shift. Let us consider we have a signal x of n and the DTFT of that signal is x of e to the power of j omega. Now, if we shift the signal by n naught, that is x of n minus n naught, the Fourier transform is equals to e to the power of minus j omega n naught into x of e to the power of j omega. So this is the first property, that's the time shifting. The next property that we have is frequency shifting. For example, if we have a signal in this manner, that is e to the power of j omega n into x of n. So the Fourier transform for that signal is x of e to the power of j into omega minus omega naught. Okay. So next is time reversal. For example, we have a signal x of n and the Fourier transform for that signal is x of omega. Now, if we have a time reversal signal, that is x of minus n, so what you do, just replace omega with minus omega. So we have, if we have a signal x of minus n, so the Fourier transform for this signal is equals to x of e to the power of minus j omega. Now let us consider, we have one problem. We have, I think you all remember that Fourier transform of a of n, u of n is equals to 1 divided by 1 minus a to the power of a into e to the power of j omega. This we have done previously. This is the problem. We have a signal a to the power of n un, and the Fourier transform is 1 divided by 1 minus a into e to the power of minus. These formulas are very, and this question are very fundamental. So it's very good if we keep in our head what is the value, what is the Fourier transform for such signals. Now the problem that we have in our case is x of n is equals to a to the power of minus n u of n. So just applying, and if we remember what we have, if we have the Fourier transform for signal e to the power n u of n is 1 divided by 1 minus e to the power of j omega. So Fourier transform for this signal, that is a to the power of minus n u of minus n, is 1 divided by 1 minus a into e to the power of minus j omega. Okay. So this is the a to the power of minus n u of minus n, it is equals to 1 divided by 1 minus a into e to the power of j omega. So this is the Fourier transform for this, and this is the Fourier transform a of n u of n. So the next property is linearity. If we have a signal x on n, the Fourier transform is equals to x1 into e to the power of j omega. Then at the same time we have another signal x2n, whose Fourier transform is given by x2 into x2 of e to the power of j omega. Then the Fourier transform of a into x1n plus b into x2n is given by a into x1 of a to the power of j omega plus b into x2 of e to the power of j omega. So this is a linearity property of Fourier transform. So we have another property. The next one is conjugation and conjugate symmetry property. For example, we have a signal x of n, but the Fourier transform is given by x of e to the power of j omega. So x star n, the Fourier transform x star n is given by x star of e to the power of minus j omega. Okay. So these are very simple properties. You can even try to prove them by yourself, and in case of any queries you can mail them. I have actually given you the email ID in the previous class, I think, isn't it? Okay. So the next property, that's the differentiation property. For example, again the problem is the same as before. We have a signal x of n, discrete time signal, and the Fourier transform is given by x of e to the power of j omega. Now n into x of n, the Fourier transform is given by j into d omega of x into x of e to the power of j omega. So this is the differentiation property of Fourier transform. Now, for example, we have a difference equation that is equals to x of n minus of x of n minus 1. So the Fourier transform for this signal, it is given, we have x of n, which is equals to x of e to the power of j omega, and x of n minus 1. By time shifting, we can write e to the power of minus j omega n, and n is equals to 1 into x of e to the power of j omega. So ultimately, if we take x of e to the power of j omega common, we have 1 minus e to the power of minus j omega. So this is the differentiation property of Fourier transform, and this is the last one, which is the Parseval solution, that is very important in solving a couple of problems. So this is also given as a property here. So if we have a summation in this manner, this is actually a proof which you can even try by yourself and try to solve it out. The proof is as follows. Summation of n equal to minus infinity to infinity, n equal to minus infinity to infinity mod of x of n the whole square is equals to 1 by 2 pi summation of 2 pi into modulus of x of e to the power of j omega whole square of d omega. So this is the Parseval's relation that we have in our case. Okay, then we will solve a couple of problems, the problems that we have left in the beginning. So this was done. So this is the this is another problem that we have. This is another problem we have. What I said is we have a signal x of n, which is we have a signal x of n which is equals to u of n minus k. When u of n minus k is what? It is a shifted, what I said, it's a shifted unit step function. Now x of e to the power of j omega, this is equals to n equal to minus infinity to infinity x of n into e to the power of minus j omega n. Okay, so if I draw this unit step function, what will happen? An original unit step function, that is u of n, lies from 0 to infinity, but the shifted one, so its value will lie from k to plus infinity. So replacing the or changing the limit, we have n equal to k till infinity into e to the power of minus j omega n. Now putting the value, we have e to the power of minus j omega k into j omega k plus 1, k plus 2 till infinity. Now just take e to the power of minus j omega k common. What will have 1 plus e to the power of minus j omega plus e to the power of minus 2j omega plus till infinity. So what we have, e to the power of minus j omega k, again using the summation formula for infinite series, we know 1 plus x square plus till infinity is equals to 1 divided by 1 minus x. Using the same formula, we write e to the power of minus j omega k into 1 divided by 1 minus e to the power of minus j omega. So this is the DTFT for the shifted unit step signal. Similarly, you can find the similarly we can find the solution for the any step. For example, you can replace the value of k with whatever values you want, for example 5, and then find out the values. Okay, I also have an alternative solution for this problem. We all know, for example, the problem is stated, the problem that I stated before is the same problem. We have a unit step and we have a shifted unit step, for example u of n minus k, and we want to find the Fourier transform of u of n minus k. Okay, so at that time what I solve the initial method or initial process, it is same. We can also have an alternative method. We just studied the property of time shifting, that is, if we have a signal x of n and the Fourier transform is given by x of e to the power of j omega, and now for example we have a signal of x of n minus k. I have classed these x of n minus k. So the Fourier transform for that signal is given by e to the power of minus j omega of k x of e to the power of j omega. Similar, so by using this, so we all know the Fourier transform of u of n. U of n minus k is given by e to the power of u of n minus k, the Fourier transform is given by e to the power of minus j omega k into Fourier transform of u of n. So the Fourier transform of u of n, it is given by 1 divided by 1 minus e to the power of minus j omega. So you can see that we can solve this problem by different means, and it's a much simpler process than the previous one. Okay, so this is fine. So let me have another problem. So this is not a signal. I won't say this is not a signal, but this is simple. This is a simple sequence. we have a simple sequence and we want to find the DTFT for this simple sequence. And the sequence is given as follows: 1, 3, minus 2, 6, 7. 1, 3, minus 2, 6, 7. And the arrow sign indicate that the value at n is equals to 0 is 1. That's the reason for giving the arrow sign. The arrow sign indicates that 1, the amplitude is 1 for n equal to 0, and obviously it is 3 for n equals to 1, it is 2 for n equal to it is minus 2 for n equals to 2, it is 6 for n equals to 3, it is 7 for n equals to 4. Fine. So writing the fundamental formula again, that is x of e to the power of j omega, that is equals to n equal to minus infinity to infinity x of n into e to the power of minus j omega n. So what we have? We have values at n equal to 0, 1, 2, 3 and 4. So which is equals to x of 0 into e to the power of 0, which is equals to 1, plus x of 1 into e to the power of minus j omega, plus x of 2 into e to the power of minus 2 j omega, plus x of 3 into e to the power of minus 3 j omega, plus x of 4 into e to the power of minus 4 j omega. So the value of x of 0 is equals to 1, the value of x of 1 is equals to 3, the value of x of 2 is equals to minus 2, the value of x of 3 is equals to 6, and the value of x of 4 is equals to 7. So replacing this value, we have the DTFT for this sequence, which is equals to 1 plus 3 into e to the power of minus j omega minus 2 into e to the power of minus 2 j omega plus 6 into e to the power of minus 3 j omega plus 7 into e to the power of minus 4 j omega. Okay, so this is the ultimately the Fourier transform for this sequence. So I would like you to solve another problem. For example, if I have a signal x of n, and the signal x of n is not a simple delta function, that is a impulse function, but in other words it's the shifted impulse function, that is del of n minus 2k. And what's our objective? And our objective is to obtain the discrete time Fourier transform. Please, I would like you to solve this problem by your own. Okay, so I think the problem is clear. There is no much differentiation here. Just it's a shifted impulse instead of a impulse at n equal to 0. Fine. Please solve this problem by your own. I have another problem for you. I would also like you to solve this problem. Okay. Okay. So this is another problem that we have. Just let me show. Sorry. This is another problem that we have that I'll just will explain to you. Let us have another problem. I think this is the problem which was actually solved in the class, but I will try to I would like you to I'll just try to describe the problem once more. We have a signal x of n, and the signal x of n is actually equal to a to the power of mod n, and ultimately also we have the value of that is mod of a is less than equal to 1. Fine. So this is the equation that we have. X of n is equal to a to mod of n, and mod of a is less than 1, means ultimately a will have values from less than 1, and it can be either negative or positive. Okay, a will have some fractional values, it can be negative, it can be positive, that's fine. So this is the condition that we have, and our objective is to obtain the DTFT, that is discrete time Fourier transform, for this. So we have to understand how can we break this signal and try to bring this signal in the form that we know, so that we can make it simple and then solve it easily. We can do it through other means. This is one method of converting the signal that is given to us to a form that whose Fourier transform is actually known to us beforehand. Okay, so before explaining this problem, I will just tell you what is u of n. This is, but what is u of n? U of n is actually a signal which will lie from 0 till infinity. Keep in your mind that u of n will have value from n equal to 0, will have value at n equal to 1 till infinity. At the same time, u of minus n will have value from n equal to 0, n equal to minus 1, n equal to minus 2, n equal to minus 3 till minus infinity. So this is u of minus n. Okay, and here we have mode of n. Mode of n. So ultimately, how can we break this signal? We can break this signal in this in the form as this is equals to a of n u of n plus a of minus n u of minus n. So if we write this, it will, because a mode of n means it will cover the entire range from minus infinity to infinity. So we can write this signal in the form of a to the power of n un plus a to the power of minus n un u of minus n, because these are the forms of the signal whose discrete time Fourier transform we know beforehand. But when we write this a of mod n in this form, the problem that we encounter is we consider the value of n equal to 0 two times. How is it? In the first term, that is a of n u of n, we have considered the value from n equal to 0 to infinity. Again, when we consider a of minus n u of minus n, we have again considered the value from minus infinity till n equal to 0. Means we have to separate, or we need to subtract one value from this entire equation, that to the value of n equal to 0, because it is considered two times. So that's the reason we have written minus of del of n. And we also know the Fourier transform or DTFT for this signal, that is the impulse function del of n. Okay, I think it's pretty clear why we have how this signal is actually broken down into three components. The first two components I described, because the range of the signal is from minus infinity to infinity, so you can write u of n, u of minus n. That's very much, and it's very pretty clear. But why we have subtracted and del n should be maybe a bit of confusion, I don't know. The important thing why we have done is because we have considered the value of n equal to 0 two times in this problem. From, that is, in the first term there is a of n u of n and a of minus n u of minus n. So as to solve this problem, we subtract an impulse term, that is del of n, and we know the Fourier transform for each of the terms. So Fourier transform a of n u of n is equals to 1 divided by 1 minus a of e to the power of minus j omega, and a of minus n u of minus n is equals to 1 divided 1 minus a into e to the power of j omega, and the Fourier transform of del of n is equals to 1. Okay, so this was an interesting problem which I felt, and just I wanted to describe the problem once more in case it was not clear. If it is clear, obviously it's well and good. So just try to simplify this equation and get your answer and obtain, and then you will actually obtain the Fourier transform for this signal, that is a of mod of n. So we have another problem that I will actually try to do it for you. I'll try to actually basically explain the problem, and then maybe you can try it out in your home, and in case of any doubts or any problems, you can obviously get back to me anytime through mail or maybe in the next class. So It's a very interesting problem. I actually like the problem. So I would like you to solve it, and then I will solve it if you have any problem. So the problem is as follows. So here we have a signal x of n. Obviously we have x of n, and our objective is to obtain the Fourier transform the signal, that is x of e to the power of j omega. So that's the objective that we have. We have to obtain GTFT, and that's the objective for the entire class actually. So it's fine. So let me define or pose the problem. X of n is equals to 1 for mode of small n less than or equal to capital N. Capital N is any number. Capital N is any number, whatever. It's just a constant, and it will be denoted by anything. Here it is denoted by capital N, and it is equal to 0 for mode of n less than equal to n. So we can draw this signal in this manner. So what we have is we have a signal which is having a constant value from minus of capital N to small class capital N, and our objective is to obtain the DTFT for this signal. Okay, so what we can do is x of e to the power of j omega. So x of e to the power of j omega, what is the original formula for DTFT? It is equals to n equals to minus infinity to infinity x of n into e to the power of minus j omega. But here, as our range is from minus n to n, just check the graph, minus n to plus n. So we can write x of e to the power of j omega is equals to n equal to minus n to plus n into e to the power of minus j omega n. Just to try to break this equation and try to get the solution. I would like you to solve this by your own, and if you face any difficulty, we can get back in the next class. You can tell me what is the problem that you have faced, or you can even get back to me via mail. Okay, so this is the problem that I want you to solve. I think you all have noted noted down the problem that you have to do it at home. Okay, so these are the things that I would like you to do it actually at home. And do you have any doubt regarding this class, or any questions in regarding to the problems or the assignment problem that were given to you, or you are facing problem? If yes, you can tell me. It's clear. The problems were clear today. Okay. Also, in the last class, I have given you some problems. So, were you able to solve them? Okay. Okay. It's well and good. So, what about your assignment? How is it going on? Is it okay? I have checked the assignment problem for week number 4, and I think it's pretty clear actually. It's not very difficult. Did you check it? Okay. You got a brief idea about DT. Did you check the week 4 lecture before? Okay, fine. So just check those assignment problems. I don't think those are actually. I checked it. I think it's pretty easy actually. Week number 4. I don't think you will face much problems. So try to solve it. Any problem, then we can obviously we'll meet in the next week, and then obviously you can get back to me anytime via mail. Okay. And this is one assignment problem that I have given you, that is x of n is equals to a impulse function, but the shifted impulse, and this is another problem. Kindly try to do it in your home. Okay, then if no doubt, I think we can end the class for today.